Thank you, Clément, and welcome everybody. Thank you for coming to see these lectures. Yes, so this is the third one. I just made a very small change in the title, including the word colloidal, because I'm going to focus mainly on colloidal composites. Okay, so my talk was almost ready, but then I had the opportunity to read a small booklet where there was a big source of inspiration again. And well, so we all know that Clément Sanchez is the world expert on hybrid materials. And the question now is there a difference between hybrid and composite? Probably there is, and I'm not going to enter very much into this, otherwise I will not tell you the story. But in that booklet, which I definitely recommend for those of you who can read French, I guess all of you better than me. Well, so there you see not only the description of what hybrid materials are, but also, you know, concepts, preparations, applications, a lot of different things. I had the impression that this story was more focused on hybrid relating organic and inorganic. What I define by nanocomposite is in a way also similar to that. For example, polymer nanocomposites, where you introduce nanoparticles into polymer templates or substrates. But it's not necessarily organic-inorganic. It can also be inorganic-inorganic if you introduce, for example, nanoparticles inside an oxide matrix, for example. But anyway, I think this would be a good introduction for the concept. And this is a review we published recently where, among other things, we describe different possibilities of how to embed colloidal particles into polymeric films, bulk, or even colloidal frames based on either doing the polymerization in the presence of the particles, or a preformed matrix where you infiltrate precursors and then synthesize directly inside of the matrix, or you have already the particle functionalized with something that is compatible with your polymer, which has been pre-made, and then you mix them, or you have a preformed matrix and then the particles are sort of infiltrating inside of the matrix. There may be other ways of doing this, but I think these are the main preparation techniques. I already showed you in a previous lecture an example of this, where we were mixing gold nanorods with polyvinyl alcohol in an aqueous solution and then drying everything together, obtaining a mixture that looks like this, where the gray part is the polymer and the darker areas are the nanoparticles. And then after stretching, we could align them and then demonstrate the anisotropic response of these gold nanorods in the presence of polarized light. Actually, this work and a few others which were going in the similar direction, I think was also an inspiration, for example, for this other paper that came up a bit later in a much more popular journal, where these people in Australia described the possibility of introducing nanoparticles with different aspect ratios and then writing patterns by manipulation with light, either by reshaping or by fragmentation of the particles, depending on the type of illumination, and also playing around with the focus so that they could write in different layers of the polymer substrate, and then read also with polarized light. So they called it, I think, 5-dimensional information storage. And there are many other examples where people have been working on introducing information into nanocomposites and then reading or, you know, creating patterns for anti-counterfeiting or for a few other applications. Okay, so this is all very interesting, but as I said, today I would prefer to focus mainly on colloidal nanocomposites. Initially polymer. I will also speak a little bit about inorganic later on. So again, the fabrication can be done in sort of related ways to what I explained for the bulk, we could say, nanocomposite materials. And then you can also obtain different configurations, either incorporating single particle, multiple particles, which are either embedded in the matrix, or they can even be floating around inside the matrix. I also showed you last week how to incorporate multiple nanoparticles into a polymer, then cover with an inorganic shell, remove the polymer, and have the particles floating around inside of the shell. So this is quite interesting because also it offers possibilities for a variety of applications. Okay, so let's start with poly-NIPAM. This is poly-N-isopropyl acrylamide. Probably many of you are familiar with this polymer, which is known to be, in principle, responsive to changes in temperature, but can also be made responsive to other stimuli. And the nice thing is that by this external stimuli, you can play around with the level of porosity in the polymer. So you can promote phase transitions. Something like this. For example, you have a spherical particle in dispersion, and then by changing the temperature, you can make it swell or collapse, so that you're changing as I said, the size of the pores. And this is driven by a phase transition where at low temperature, typically, these particles are hydrophilic, and they become less hydrophilic at higher temperature, so they collapse because the branches of the polymer prefer to be in contact with other branches of the polymer rather than with water. And as I said, by playing around with additives, you can make them sensitive to pH or to ionic strength or to a few other things. Now, typically, you would see plots like this to define the thermal sensitivity, where, for example, you start at low temperature, at large particle size, and then as you increase temperature, there is a gradual decrease, but then suddenly there is a well-defined temperature at which there is a sudden drop, and this is the phase transition temperature, which is typically called lower critical solution temperature. In other papers, they call it a bit different, but it's always marks the transition between hydrophilic and less hydrophilic. Okay, now, why are we interested on this? Well, we are interested because you can also try to play around with the plasmonic particles and make them, convert them into nuclei to grow the microgels directly from them. So this was a piece of work that we did already a long time ago when I was still in Vigo, where we found a way to use the famous now, for all of you, bilayer of surfactant on top of the metallic particles, which contains, as you know, an interdigitated region, which is hydrophobic. And so in that region, you can also infiltrate organic molecules, hydrophobic organic molecules, like styrene or divinyl benzene. And then you can promote reactions and polymerization directly at this interface, and then obtain very well-defined polymer coronas on top of the metallic particles. And once you have polystyrene there, then you can use this as a suitable nuclei to promote the polymerization of poly-NIPAM, and then you obtain particles like this, okay? And you will tell me, or I would say, they don't look very nice because the shells don't look very spherical, right? Well, this is, of course, a sign of the flexible nature of these shells, because when you are looking at them in the electron microscope, they basically collapse because there is no water inside. So what you see is actually something like a fried egg. And in fact, if you now measure the optical spectra by changing temperature, in principle, you don't see much, right? So you see just a small redshift of the position of the maxima. If you remember, this is related to a gradual increase in the refractive index of the material around the particle. But now if you plot the maximum position versus temperature, what you find is also a very well-defined jump in the position of the peak, which correlates perfectly with the lower critical solution temperature. Okay, so now you already have a first application. You can use now plasmonics to detect the transition temperature for these microgels. Now, another interesting point is if you play around with the concentration of the cross-linker, you can also make the shells more flexible or more rigid. And so by, as you can see here, 5%, 10%, 17.5%, the shells look like larger or smaller because they collapse more or less. And if you look at them in the atomic force microscope, then you see that at low cross-linker density, the core seems to protrude out very clearly from the shell, so it's totally collapsed on top. But for the larger cross-linker concentrations, the position of the bumping of the core is less and less defined. And this is also related to the changes in the diameter and so the swelling degree of these shells, which are decreasing as you increase the concentration of the cross-linker. And this is not only nice to see in pictures, it's also relevant for one of the applications I'm going to tell you in a minute. Another interesting point is that once you have the plasmonic particles inside of a porous shell, you can actually use the pores as channels through which chemical reactants can diffuse, so you can perform chemical reactions directly on the core. And so you can think, for example, of making these particles larger when they are already encapsulated. And that you can do by doing the seeded growth reaction at high surfactant concentrations. Interestingly, if you use a lower surfactant concentration, they also grow, but they form tips. So they become sort of star shape, and that you can also see by a clear shift in the position of the plasmon resonance. And then both of them would redshift when you change temperature, but in a different degree. So these ones also become a bit more sensitive to the changes in the refractive index, which is in agreement with the theory that I explained on the first lecture. Okay, now what can we do more with these particles? So we can think about using them for catalysis. This is a very simple catalytic reaction, not very popular. In fact, I forgot to write the reference of the review. We have a review published in Chemical Society Reviews in 2012, which is describing more in detail the mechanisms by which metal particles can catalyze these sort of electron transfer reactions. And so here we have a reaction where sodium borohydride should be able to reduce ferricyanide into ferrocyanide. But if you try to do this in water, it's extremely slow. It takes even days, and it's a zero-order reaction. However, if you do it in the presence of even spherical gold particles, the particles sort of act as an electron transfer mediator and catalyze the reaction. So it becomes much faster and first order in ferricyanide. So now it's actually much easier to follow, and you can also observe different effects by using this reaction as a model catalytic reaction. And so what happens if you do it with the polynipam coated gold nanoparticles? What happens is that depending on temperature, the reaction rate is changing in a very weird way. So you would expect by the Arrhenius law that by increasing reaction temperature, you would have a gradual increase in the reaction rate, right? So in fact, what we see are three regions where initially the reaction rate is increasing, then it's actually drastically decreasing, and then it's slowly increasing again. Any ideas why this is happening on the basis of what I told you about the behavior of these particles? I guess you all know, but I will say it anyway. So here Arrhenius is dominating, so we have an increase in the reaction rate with temperature. Here we have the collapse of the shell, so the pores become very small, the diffusion is much lower, and this is dominating the reaction rate, and so this is why we have a drastic decrease in the reaction rate. So this is now diffusion limited kinetics. And then we have already fully collapsed shell. And then again, by increasing the temperature, Arrhenius is dominating again. And even though the diffusion is low, the reaction is faster at higher temperatures. Okay? Now, a bit more complicated. We do the same, and this sort of correlates again with the solution transition temperature. We can do that for different degrees of cross-linking density, and then again we find a different degree of swelling in each of them, as I mentioned earlier. And then we also see that, so this would be similar to this one. And then for a higher cross-linker concentration, we see a much lower change in the reaction rate, but following more or less the same trend. And for a lower cross-linker concentration, we see, well, what we expect, right? And so from the higher to the lower, we see almost 1 order of magnitude change in the reaction rate. All right, now let's go to a different potential application. Raman scattering. I think I didn't introduce this properly in the last lecture, but anyway, I will repeat it if I did. So you all know about vibrational spectroscopy, right? So you know that with infrared radiation, you can excite vibrations of different bonds in molecules. And so you can watch the transition to different vibrational states by recording an infrared absorption spectrum. And this is very selective because it provides sort of the vibrational fingerprint of your molecules. But if you want to work in water, this is a problem because water absorbs quite a lot of infrared light as well. And this is why Raman scattering spectroscopy has been proposed as a more useful technique when you're going to work in water, because water also scatters Raman, but much less intensity. Now, the issue is with Raman, you're exciting electrons from the ground state to either allowed or forbidden electronic state. And then you watch the emitted electrons or scattered electrons when they go back to the ground state. But if you want to have Raman, they should go to a different vibrational state. And so if you start on the very ground vibrational state, the Stokes scattering would mean that the electron goes back to a higher energy vibrational state. If you start at an excited vibrational state, you can also watch anti-Stokes, meaning that the electron goes back to a lower vibrational state. So as I said, this can also be done for allowed electronic states, and this is what we call resonance Raman spectroscopy. And this is, of course, a much higher probability process because we have an allowed state here, okay? But anyway, in all of these processes, the Raman cross-sections are extremely low. So this is a comparison of the, say, cross-section of different spectroscopy techniques. So you see Raman is the less efficient one, and then you have Rayleigh scattering, resonant Raman, infrared, fluorescence, UV, and here come other techniques that we didn't know yet, which are the surface-enhanced Raman scattering or surface-enhanced resonant Raman scattering. And in the ideal case, you can have a cross-section which is even higher than that for UV spectroscopy. So, this was discovered in 1974 in the group of Fleischmann, who is also well known for another discovery which turned out not to be so spectacular as he claimed. But anyway, so this was true. What Fleischmann observed was that when they were measuring the Raman scattering of pyridine, and they did it on top of a silver electrode, then the intensity that they obtained was many orders of magnitude higher than the one for the pure compound. And the explanation that they found was mainly that the electrode was very rough, and so many more molecules would be adsorbed because they were following like the roughness of the substrate. So somebody did the numbers later, and it turned out that this would not be possible to obtain the intensity that they got. And then a few other people came very quickly on this topic because it was found to be very interesting. And there were two main schools proposing the explanation for this phenomenon. One was called the chemical effect, mainly described by Andreas Otto. And so Otto said that the metal is basically facilitating, again, electron transfer or energy transfer between the different energy levels of the molecule, and this is why the probability of this transition would be much more favored. The other school is called the electromagnetic mechanism, which was almost in parallel described by Van Dine, Creighton, and Moskowitz. And this claims that it is the enhanced electric field that we find for the plasmonic effects, which is changing the polarizability of the molecules that are located next to the surface of the metal. And by increasing polarizability, you're enhancing a lot the probability of the Raman scattering process. Now, it's now mostly accepted that both mechanisms can play a role, and in fact, you can find chemical effects in materials that are not metals. So this is an evidence in favor of this mechanism. But this mechanism is accepted to play the major role in this process. And this is why we are working a lot on this type of spectroscopy. Okay, so we have our metal particles, we irradiate, we create a distribution of enhanced electric field, which is much higher close to the surface. It decays very quickly away from the surface. And then we have molecules which are attaching to the particle, or at least located very close. And then the electric field is affecting the polarizability, and you obtain, again, a vibrational fingerprint at much higher intensity than you would obtain for the isolated molecules. If you play around with the morphology of the particles, you can increase the efficiency of the enhancement of the electric field. So it's well known that for particles with sharp tips or edges, you can obtain much larger enhancement of the electric field. The trick here is that in order to exploit these very high electric fields, you need the molecules to come exactly to the tips or exactly to the edges, because otherwise they will be in regions where the enhancement is almost negligible. Another way to do this is bringing particles close to each other, and then you have to bring the molecules at the gaps between the particles, because there is where new coupled plasmon modes would create a very large electric field, and then you would increase the signal. So this actually is a real example where we had isolated gold spheres floating around in solution in the presence of a molecule, and then the signal was extremely low because isolated spheres are not very efficient, at least small ones are not very efficient as Raman enhancers. But as soon as you aggregate them by simply adding, for example, sodium chloride and increasing the ionic strength, then they would form aggregates. The molecules which were already adsorbed on the surface would sit at the gaps between the particles, and then you immediately can record this very clean and well-defined spectrum from the solution. Okay, I will tell you more about Raman scattering next week. Today I will basically show an example. But if you want to learn more about these fields and the recent progress and prospects, I would recommend to read this paper. I'm sorry, it's a bit long, but most of the big players in the field contributed to it, and I think it is reasonably well sequenced and covering most of the important aspects of the field. All right, in my own view, CERS has a large number of advantages that should allow it to become a routine analytical technique. But unfortunately, there are also still some problems that need to be resolved properly so that the users will rely on the technique. And so, the advantages I almost said: high selectivity, high sensitivity. You can do very fast measurements if the sensitivity is good. You can even use portable instruments. You can encode particles, and I will also tell you a bit about this later today. And you can apply it to almost everything because almost every molecules have Raman signal in principle. But you have to be careful to obtain sufficient reproducibility, uniformity of the substrates that you use to enhance the signal. As I said already, the molecule has to be as close as possible to the metal particle, which is not so easy to achieve in some media. You can also contaminate the signal if other molecules are floating around in the same system, and this is particularly relevant in biofluids, where you almost always have contamination from proteins, lipids, and many other things which are present in the biofluid. And you can also have so-called memory effects that may force you to use a new substrate every time you want to do a measurement. Because if the molecules that you're measuring at time 0 are staying on the particles, if you measure at time t, you will also record the molecules that were present at time 0. So I will tell you more about this next week, about how to resolve it, I mean. Okay, so back to polynipang and gold. So we have these particles, and we take care that the cores are big enough that they may be sufficiently good enhancers of the Raman signal. And now what we want to do is to detect molecules like naphthalene thiol. And so the idea is that we play around with the porosity of the shell so that we can allow or forbid, or at least reduce the diffusion of these molecules through the pores coming to the core. So first of all, demonstration that we can use these particles to measure this molecule. So this is a comparison of the Raman spectrum in blue of the pure molecule, and in red we have the surface enhanced Raman signal in the presence of these particles at low temperature, meaning that the molecules can freely diffuse through the big pores and attach on the core through this thiol group here. And in fact, one of the differences between these two spectra is that we can measure this peak, which corresponds to the thiol vibrations. We can measure it for the pure molecule, but not for the molecules that have bound to the metal particle. Now, what happens if we measure by starting at low temperature? So we record a big signal of one of these peaks, and then we increase temperature, so we collapse the shell. What happens is that nothing changes because the molecules remain inside and they are bound through the thiol, so you still record a high intensity. If you now lower temperature and swell the shell again, nothing happens because the molecules stay there. If you do the experiment starting at high temperature, meaning that the particle will be at this state, initially you measure a much lower intensity because, as I said, the molecules have more trouble to diffuse through the shell, and so the number of molecules that are in the neighborhood of the particles is very low. Now, without changing anything, you decrease temperature, and now the shell swells, the molecules can diffuse, and you obtain again a high intensity like before. Okay, now, if you try to do the same thing with a more difficult molecule like naphthol, and I say more difficult because here there is no reason for this molecule to stay bound to the metal particle. So what happens is, at low temperature, we can record a little bit of the signal in our view because the molecules can diffuse through the pores, but they are coming in and out freely. And so there is some possibility, some probability that some molecules are present close to the core when you do the measurement, and so you can get some of the peaks at low intensity. Now what happens when you increase temperature is that now suddenly the intensity of the signal increases drastically, and this is probably related to the hydrophobic nature of the molecule. And so when you're driving the transition between hydrophilic and less hydrophilic, then the molecules are more confident to be close to the core, and in fact the shell is also much smaller, so you have more molecules providing signal close to the metal particle. And then what was very striking was that if you now lower temperature and swell the particle again, the molecules diffuse out and you lose the signal. Okay? Another interesting example comes from a molecule that is not only a Raman active but also fluorescent. And so, so this is the emission spectrum. And now you can do the experiment again at different temperatures. And what we found is a low temperature. There is, again, little diffusion and not very much absorption on the core. And so we measure mainly fluorescence. At higher temperature, the molecule accumulates, so fluorescence is quenched by the metal particle, and we are enhancing Raman. And then when the molecules diffuse away, you measure again fluorescence, but some of the molecules remain, and so we have some peaks which are related to Raman on top of the fluorescence spectrum. And if we start at high temperature, again, initially we measure only fluorescence because the molecules don't diffuse in. At higher temperature, some molecules diffuse in. This is after some time, the molecules diffuse in, and then we have a little bit of the peak. And then at higher temperature, we are trapping, and we obtain again the Raman signal mainly. So this is a sort of concept for a reusable Raman enhancer, which can capture molecules that will not bind to the core, and then release them, and then ready to be used again. If the molecules are remaining on the core, then, as I showed you in the previous slide, you have the problem of the memory effect, because they will always stay there. Now, you can even improve the system by playing the trick of the in situ growth. For example, growing a silver shell on top of gold nanorod cores. And then we observed higher sensitivity for the same type of analysis. And you can also play a trick of depositing magnetic particles on top, and then you can collect them with a magnet. And then if you measure at the spot where the particles have been collected, then of course the number of particles, and so the number of molecules on particles is larger, and so you can obtain a much higher sensitivity by playing this trick. Okay? All right, any questions so far? Yes?
Why we don't have the signal of the polymeric shell in the Raman or surface?
That's a good point. So styrene actually provides a rather good Raman signal. We never have been able to see a strong signal in polystyrene. So it might be that the polymeric shell that is covering the cores before the polymerization is sort of screening the contact with the metal particle, and we don't see much effect of the polymer there. But it's a very good point, and we never understood it very, very well. But this is what we find in practice, that the polymer is not providing a sufficiently strong signal. Yes?
How many measurements can you perform with one batch?
Many, because so it depends what type of sample you want to measure. But typically these measurements, if you do them in solution, you only use like 1 or 2 milliliters. The production is done in hundreds of milliliters. And you can even fabricate a larger concentration and then dilute in little batches, depending on the concentration that you want to detect and the signal that you can obtain.
And the shelf life is?
The shelf life is very long. This polymer is very stable. In fact, it's you could say it's too stable because it's not biodegradable. So for some of the drug delivery applications, this is not a good polymer. Yes? Right. Yes, so we have done several cycles. I don't know how many times you could use it, because if you're doing this without cleaning the system, then you might have still the other molecules floating around. But what you can do is you open the shell, you measure, record to see that the molecule has diffused out, centrifuge, and then redisperse in the new solution. Okay, let's move to a slightly different concept. Encoded particles. Okay, so this serves also as an introduction for next week, but I wanted to show you that these particles can also be used for this application. So the concept now is, you know that fluorescent molecules are very often used as labels, very much in biological studies, but in many other fields as well. There are many different dyes, and you can obtain different colors if you illuminate and obtain luminescence at different positions in the visible spectrum. But the emission bands are typically rather broad, right? So the number of colors that you can use at the same time is a little bit limited. Another issue is that if you illuminate for a long time, molecular dyes typically bleach, meaning that you are losing gradually the intensity of the emission. So why not use Raman as a label? And so you can make metal particles, you can tune the morphology to make the most efficient ones as you like, and then you can cover them with molecules that we call Raman reporters, which have a high Raman cross-section and a very well-defined vibrational fingerprint. And so these would be our labels, which will not bleach, so can be used for a very long time. And the spectra have very narrow peaks. So in principle, you could think of making large libraries of these codes. You may think there may be an issue if other molecules are floating around. They could also come and bind to the particles, so they would change the spectrum. So to resolve that, what you can do is to cover the encoded particles with a protecting shell, so that when the particles are protected, other molecules can come to the shell but will not diffuse in, and so you will not measure any other molecules. And then if your shell allows, you can also functionalize it additionally with, for example, antibodies or other biorecognition molecules, so you can selectively bind these particles also to a biological target, or you can embed it in a banknote and create anticounterfeiting additionally. And so, well, so this will come for tomorrow. So this is one of the projects that we are trying to do, labeling cells, culturing them in 3D, and trying to do confocal Raman to study processes, biological processes in a system that try to reproduce a human body. Okay. So the same system I was describing. You have gold particles, whatever shape. You cover them with the polynipam. You infiltrate a Raman dye. We do it this way because if you attach the Raman dye before the encapsulation, it may affect the polymerization process. But the porosity is big enough so that they can diffuse. And of course, we can use any molecule we like, and so we choose them with a thiol group so they will bind and stay there. And then you can wrap the particle by, for example, layer by layer assembly, so that you close the pores, and then you can bind antibodies. And so the particles look like this, and you can infiltrate different dyes, for example, Astra blue, Nile blue, and malachite green. And so you obtain different Raman spectra that you can distinguish, and even in a mixture you can see peaks which are characteristic of each of the labels that we have there. And because the shells are big enough, there will be no signal from other molecules coming from the outside. All right, so this is one example where we had two types of cells. So one was a cancer cell and the other was a fibroblast. And we had the encoded particles with one of the molecules. We had the three labels coded with the same antibody, which would recognize only the cancer cells. And so after incubation, we obtain, we see fluorescence by using also a fluorescently labeled antibody. And we measure spectra at the stars in white and at the stars in black. And so at the stars in white, we measure these different peaks which come from the different dyes that we are incorporating inside of the particles. From the cells in So from the stars in black, we don't measure any signal, meaning that the particles have not bound there. Okay. Now, if we want to use the different signals at the same time, we can code them with different antibodies. One which will bind to both the cancer and the healthy cells, one which will bind only to the cancer cells. And then again, by playing the same trick, we can distinguish this will be the cancer cells because we see the 3 signals there. This will be the healthy cells because we only see the signal for the label that is coupled to the antibody that will bind anyway. Okay? So in principle, we could do this with multiple labels and trying to target different cell lines. And I'll show you an example next week. Another possibility, and I wanted to show you a different type of hybrid system for the same application. So this is based on the very well-known galvanic replacement reaction, which is based on the oxidation of silver by gold 3. And so if you have initially silver nanorod, sorry, this is a silver-coated gold nanorod, and then you play this reaction on the outside, then you start transforming the particles into an octahedron, which has a gap inside and a gold nanorod inside. And the silver has at least partly been etched away by this process where you are oxidizing the silver atoms and reducing gold ions, forming this shell. So you can do that also without the central core and in the presence of different molecules. And so by doing that, so you start with a well-defined silver sphere, for example, you do galvanic replacement in the presence of a variety of molecular systems. And then by playing around with the nature, so the composition of the molecules and the mutual ratio between them, you can obtain a large number of tags because not only the position of the peaks, but the relative intensity can be well defined by the relative composition between the different molecules that you're introducing there. So the idea here is that the molecules are present in solution. When you play in the reaction, they remain trapped inside of the shell and they will not leave because these shells are continuous. And then you have a very robust system where, as you can see here, we can obtain a large number of codes from the same process. And then again, you can place antibodies and do multiplexing. Again, another different system, and then you see here the many possibilities of colloidal nanocomposites for this application. This is a system where we have a polystyrene core, which has been fluorescently labeled inside. And then by playing around with the surface chemistry of these particles, which have amine groups, we can attach very tiny, very tiny gold particles, which are covered by molecules that will facilitate internalization in cells, and in this case, gold nanostars, which will provide, which are encoded also with molecules, with Raman reporters, and will provide the Raman signal. So in 3D, the particles look like this. So you don't see the very tiny particles because they are too small for the resolution, but you see a nice distribution of the nanostars. And then you encode them with this molecule that will attach, of course, to the metal particles. And then you can see the fluorescence from the core. And at the same time, you can also localize by doing confocal Raman the particles on top of the cells, inside of the cells, and also at the bottom. So you can confirm the internalization of the particles inside of the cells. So this is a bit of a complicated system, and right now we mainly use individual nanostars as the codes, and this will be the topic for what I will tell you next week. Before going into a different topic, I would like to tell you also a little bit about a similar system where we co-encapsulate gold nanostars and also rare earth doped particles, which we use as nanothermometers. And the idea here is to try to make more reliable hyperthermia therapy systems. And so you know how this works. So the particles absorb light from your laser beam, and they release part of it as heat, so they increase temperature locally, so they can kill the cells where they are internalized or placed on top. The problem is, when you're doing this, you never know how much you're heating. And so what we try to do is to use these thermometers to measure the temperature when we are irradiating the particles inside of cells. And in order to do a more realistic system, we used cell spheroids, which reproduce a more three-dimensional system. Now, again, to protect the Raman signal and also the molecules to be more stable in colloidal dispersion, we coated the whole system with a tiny silica shell. Okay, so this is the characterization of the nanothermometers. What we use here are thermometers which have been purposely designed to be excited at the same wavelength that we use to heat the particles, around 800 nanometers, and they emit at a bit more than 1,000 nanometers, so we can detect in the near infrared. So we can use near infrared light to excite and to collect the light. And so this is fluorescence from the, in this case, neodymium, which is incorporated in a matrix of cadmium fluoride in the nanoparticles. And so from the intensity of these peaks, we can obtain, from the changes in the intensity as a function of temperature, we can have this calibration line, and we can measure the temperature locally at the place where we are heating. If you want to learn more about temperature, I would recommend these two review articles. One which is more related to nanothermometers per se, and the second, which is very recent, related to optical nanothermometry in biological systems. So anyway, so this is fluorescence from the particles, simply to show that we can obtain them from internalization inside of these cell spheroids, which are many microns in size. So these are images from the spheroids directly before the incorporation of our composite nanoparticles. These are images after internalization of the particles. So this would be the signal from the labels in the cells. And this would be the red one. The red color is how we label the fluorescence from our nanothermometers. So you can see actually these are at different depths. So we can get to many hundreds of microns of depth inside the system. And we see the incorporation of a gradually lower amount of particles as we go very deep in the spheroid. And then we can measure temperature at different intensities of the laser beam. And then we can see that depending on the concentration of particles in the system, the irradiation for different types, we can get to a plateau, or we can even get to a plateau and then to a decrease in the intensity. How do we explain that? Well, of course, the increased temperature as we increase the number of particles means that the laser is heating more particles, so they are releasing more heat to the system. And then at some point, there is a compensation between release of heat and dissipation through diffusion of heat. In this case, the intensity is so high and the number of particles so high that we actually get, at some point, we get reshaping of the particles. And so there is a decrease in the efficiency of heating. Now, another point is that also, if you irradiate the particles, you see very often changes in the cells, in the spheroids. Even in some cases, we see bubbles when the number of particles is big enough and the intensity is high enough. Another important observation is that the measurements with our nanothermometers not always correlate with measurements that are done with a thermal camera. And the reason is that the thermal camera is only measuring at the surface, while with the nanothermometers we can go inside and measure what is happening inside of the spheroid. Okay? So we are trying to incorporate this also in those scaffolds that I mentioned earlier to try to correlate temperature effects with other effects in the system. All right, one more system and then we move to something else. You remember this from last week. So we were using hydrophobic gold nanoparticles coated with polystyrene, encapsulating them in a block of polymer, and then obtaining very well-defined three-dimensional arrays of the particles. Now, what I didn't show you is that this can also be done with mixtures of sizes, so you can co-encapsulate big and small particles, which was not really obvious at the very beginning. But obviously, the dispersion, so the particles were stable enough that they were completely mixed in the solution, and so they were co-aggregating very nicely. Now, then we asked ourselves the question, can we also do this with particles that are completely different to each other? So these are rather big gold stars coated with polystyrene, and these are rather small iron oxide particles coated with oleic acid. And so, with oleic acid. And so the question is, will the hydrophobic forces will be able to drive the co-assembly of these two very dissimilar systems? And yeah, well, obviously the answer is yes, otherwise I would skip to something else. And so we do obtain particles that look like this. And they are very nice, not only because we are co-encapsulating, so now we can of course think about magnetic manipulation of the hybrid particles, but also because the anisotropy of these particles leads very often, we see, that some of the tips are actually coming out of the polymer shell, meaning that now we have the perfect system for molecules to come and bind precisely at the tips. Of course, we have to clean the system, so the concentration of these particles initially is much higher than the concentration of stars, so we also obtain lots of these micelles that contain only magnetic particles, but they can be nicely separated by centrifugation because the nanostars are much heavier. Okay? All right, so again, the nice movies from 3D. This was challenging for our colleagues because the electron contrast between the gold and the iron oxide is very different, and so they had to adjust and prevent shadowing effects and a few other things to obtain this kind of movies. But anyway, this makes us also confident that the particles are distributed everywhere and we can promote the manipulation. So you see here we can easily, with a handheld magnet, accumulate the particles on a small spot. And now the idea is we can combine the magnetic properties with the optical response of the plasmonic particles. And we plan these two types of measurements. So one is we have the particles floating around in solution, and then we measure at some spot inside of the dispersion where they are basically like individual nanostars. And otherwise we collect them with the magnet, and then we measure precisely at the place where all the particles are together. And also, you remember I mentioned, I think in the first lecture, that when gold nanostars are aggregating very close to each other, you can have destructive interference and lose the signal. But here they are protected by the polymer shell, so we cannot get this destructive interference. So if any, we can obtain constructive when the tips are coming next to each other. Okay, so this really works very nicely. So we obtain very little signal for the particles in dispersion. So this would be these lines here. Then when we create the, my mistake. So these are the measurements without the analyte. And so coming back to your question, there is no signal from the polymer either here. When we introduce the malachite green, because of electrostatic interaction, it's absorbing on the particles that are negatively charged. And then we obtain already some signal, which would be good enough to detect this concentration. But now with the magnet, we obtain a much larger intensity, meaning that we can lower dramatically the sensitivity of the measurement. Okay. All right, so coming back to the inspiring booklet by Professor Sanchez, and in particular by the hydrolysis of silicon precursors or iron oxide or metal oxide precursors in general. And of course, this the formation of silicon oxide by using the chimie douce is extremely well known and applied both in bulk, in thin films, and in colloidal state for many years. And so this brought to my memory one of my first popular papers where I was making gold particles. This was a discovery, as I mentioned. Now this is completely routine and even done as an exercise for undergraduate students. But at the time, being able to obtain the red dispersion was really striking. And then after many attempts, we came up with the idea of using so-called silane coupling agents, which have, for example, an amine group on one side and a silicon hydroxide group on the other side. And so the amines are likely to bind these citrate capped particles. And then you have the silicon oxide, which allows you to grow uniformly silicon oxide on top of the cores. In fact, this initial shell we did by mixing the APS-coated particles with sodium silicate at the right pH and concentration so that there would be condensation directly on the cores. And then these initially coated particles were used in the standard Sturber method to precipitate tetrethoxysilane, so hydrolyzed tetrethoxysilane, and condense directly on the silica-coated cores. And with this method, we could grow as large as we wanted shells on top of the cores. Then there were many other methods coming up, and this we reviewed some time ago already. So here you can find many different ways of coating metal and other particles with silicon oxide. And more recently, we also reviewed the potential applications of these particles, also covering a little bit of newer synthetic methods. So I'm not going to expand very much on this. I would like to also show you this other method. So again, this is what comes mainly from the Sanchez lab, the formation of mesoporous silicon oxide films on substrates. So I was very fortunate to have one of your grandchildren coming as a postdoc to my lab, Paula Angelomé, who did PhD with Gallo Soler-Ilia. And Paula, of course, knew how to do this very well. And the idea that we had was, now we are going to have glass. We are going to deposit our gold nanoparticles on the glass. We are going to spin coat the precursors of the silicon oxide with the surfactant to create the micelles, to create the pores. And then we are going to use the pores as templates to grow tips on the particles so that they will become more efficient for enhancing the Raman signal of molecules that then will have to diffuse through the pores. And so we can only obtain the signal of very small molecules. So that was the main idea. So let me show you on a cartoon. So this would be the porous films, this would be the particles below, and then we would have a mixture of small molecules together with, for example, proteins, and then we should be able to detect these molecules diffusing through the pores. So the laser is coming, they are being illuminated, and then they are enhancing the Raman signal, and we can detect the molecule. It works very well, right? Okay. So it also worked in practice. So this is a very nice picture of the gold particles which have been scratched from the composite film. So you can see also very nicely the well-defined pores on the silica film. And then by doing this seeded growth process that we always use, we were indeed able to obtain particles with tips. And depending on the extent of this process, they were longer or they were shorter. And so we also saw the changes in the plasmonic spectrum because of the growth of the tips. And then we also saw that the cartoon was not only working in the cartoon, it was also working in practice. So let me guide you through this plot. So this is a measurement of the mixture of BSA, a protein, bovine serum albumin, in phosphate buffer saline. and in the presence of a silica, porous silica shell. And what we measure here are mainly the signals of BSA, but also with some of, because we only have BSA. So the conclusion here is that in this case, the trick didn't work, because we should not be able to measure BSA according to the cartoon, right? If we do the same thing with a mixture of BSA and MBT, we measure both the signals of the protein and the molecule. So again, it didn't work. And so then we asked Paula, what is happening here? And she said, well, maybe we are dissolving the silica by treating it with the biofluid, which is a well-known problem. And then she decided to do the same process by using titanium oxide rather than silicon oxide. And then it did work. And so this is only MBT with in PBS with the titanium film. And then we only see the peaks corresponding to MBT. And when we do the experiment with the mixture, again, we only see the peaks corresponding to MBT. So in this case, we do not measure the signal of the protein, meaning that titanium oxide films don't degrade in the presence of the biofluids. Now, can we do this also with colloids? Right, so then it came this paper by the group of Matsuura, where they said, well, you don't need to do the pre-coating of the gold particles if you already have CTAB, because the same as I showed you earlier for the polystyrene, you can do the condensation of the tetrahydroxysilane templated by the micelles on top of the gold particles. And then you can obtain these core shell systems which have already a porous shell. Now, forgive me if I'm too strict, but these shells don't look very ordered to me. And so we changed a little bit the recipe, and I had a very talented postdoc, Marta Sanz-Ortiz, who decided to look into the literature, find recipes for films with parallel pores, and then try to implement similar conditions at a little bit higher temperature. And then she was able to obtain these very nice pictures. Again, these are tomographies coming from our colleagues in Antwerp. And you can see we can obtain not only the coating of different morphologies, but in all cases, it looks like the pores are radial coming from the core directly to the outside. And if you don't trust me, this is the tomography that shows the same thing. Again, extremely challenging, because now the electron density is very different, and we also have the pores which even lower the contrast. And so anyway, so they were able to obtain this by playing around with a few parameters in the electron tomography. And then again, we wanted to use the pores as templates to grow tips. Initially we were naive and thought maybe we can grow even silver tips, and then the system will be much more efficient. But unfortunately, after coating with silver, we still only saw nanorods. They do have a silver shell, so they might work, but they don't have the tips. And so we came back and tried the process by reducing gold, and then the tips came up very nicely, and also on different cores with different shapes. So this is a very general process. If the pores are well defined and you do the seeded growth with the appropriate conditions, you can obtain the growth of these tips, and they also look nice in 3D. Okay, now you can also compare the efficiency. So first of all, the spectra, very clear, but also the efficiency in Raman. Unfortunately, the instability of the silica shell also made us work in ethanol, and ethanol is a very strong Raman active molecule. And so we had to sort of change conditions from ethanol into mixtures of ethanol and water. And with these conditions, we obtained very low concentrations, detection of very low concentrations of this analyte, crystal violet. Okay, one more piece to finalize. I think I went a bit too long today, but I wanted to tell you a little bit about Janus particles and why they can also be relevant. Okay, so you probably all know the concept. So Janus was the god of beginnings and transitions, meaning that it had two phases, one looking at the past, one looking at the future, and this has been an inspiration for many people to create particles with two phases, with two different functionalities at two sides. And so there are many possibilities for making this type of systems, not only in plasmonics, but we have also a review, already probably too old, but showing what can be done in plasmonics. There are many different things. There is also a little bit debated work of Francesco Stellacci related to the organization of ligands on metals. So this is very well known for films. There is segregation if the nature of the molecules is different. In the case of particles, you may be able to obtain different organizations depending on the nature of the molecules and depending on the size and the morphology of the particles. But in principle, you can also obtain segregation to obtain two completely different sizes. And this is our work with two different polymers, polystyrene and polynipam, which we didn't really expect to segregate so well, but playing around with conditions, temperature, and so on, we also obtained this type of particles, which in electron tomography, by doing selective staining of one of the polymers, we can actually see almost a perfect half shell, while the other polymer is almost invisible there. And so this was published with a cover because the pictures look very nice. But these type of systems can also be used to selectively do chemistry on one side or the other. And so we were not the first. There was this paper published in 2010 where they showed that by coating particles with two different ligands, I think this was, this mercaptobenzoic acid, and this was polyacrylamide. And so depending on the position, you could grow silica on one side and not on the other, and obtain these very nice particles. So yes, and by doing chemistry there, they were also able to grow silver particles directly on top of the exposed face of the gold. So we thought, well, why not to do this, to grow spikes on one side? And is this useful for anything? We don't know yet, but it may be, depending on how you play the chemistry afterwards. But of course it worked, so we combined the method published already in 2010 with our nanotechnology paper, meaning reduction by using DMF as the reducing agent, to grow tips selectively on the exposed side of the gold particle. And then, of course, by EDX, we can observe silicon oxide and gold separated. And we obtain very nice tomography images. And probably you can do also selective self-assembly of particles on one side or exposing tips to the side. This remains to be done. And so with these images, I conclude for today. So thank you again for being here. Thank you for your attention, and I'll be happy to discuss a bit more with you.